Hi, everybody. It's time for our last lecture of the semester. I had to sort of make some decisions of where we would drop things, and I thought that this last thing, this last little innovation, would be a really good fit as a small extension of our row operations or our Gaussian elimination, and might teach you something a little bit new at the same time. Um, but there's so much more to this topic, and I'm going to list a few things at the end. Uh, so yeah, essentially what this comes down to is a method that aims to improve the amount of processing time it would take to go through the solution to a system of equations. And it turns out that you can do a little bit of a transformation in order to get to a form that makes this a little bit easier to do. And so we're going to talk about LU decomposition. It's our last topic that we'll cover this semester. This is the last topic I'll expect for your final exam. So let's get started with it. And to find my stylus here. Cool. All right, so we're going to be covering this method, LU decomposition or factorization. Either way, it's a way of solving the same sorts of equations that we were solving in that last lecture. A matrix A times some vector of variables x that we're trying to solve for equals some vector of constants b. And we're going to do this by using a substitution. Here's the idea. It's called LU because we're going to be letting A equal LU. What are LU? L is a matrix, and so is U, where L is lower triangular and U is upper triangular. So what does that mean? Upper triangular, well, we talked about that a little bit last time, right? It's when you have a matrix and the only non-zero entries are on the diagonal and to the right. So up here, I'm trying to depict this in a good way. These are the only non-zero entries are up here, and all of the bottom left corner, those are zeros. So of course, lower triangular is going to be something similar. It's not triangle. It's going to be lower triangular. A lower triangular matrix is going to be the exact same thing, except that it's going to be all of the entries along the diagonal, and to the left are the only non-zero ones. Of course, some of those could be zeros, but they're the only ones that could be non-zero. Everything above that and to the right would have to be zero. Okay? So the only non-zero entries would be in there. So that's where the triangles come from. It's everything along the diagonal to the left or everything along the diagonal to the right. And so, okay, why is this important? Well, let's think about this. If A is equal to LU, we're writing A as a product of two other matrices. A equals L times U. Let's think about this. Then we could take this equation here, AX equals B, and if A is LU, well, I can simply replace this, the A that was here, by an LU. And so what do we have? We have L times U times X equals B. Check this out. What we can do is immediately perform a two-step back substitution. Why? Well, because this here, this UX, if you take a matrix and you multiply it by a vector, you get another vector. So that means that the U times the X, this here is itself a vector. And if I have that vector sitting there, that means that I have a different system. I have L times that vector equals B, which means that I can just do a back substitution because I know that L is triangular. I can do that one component at a time. So, so here's the idea is solve LC equals whatever this thing is right here. All right, we're going to call that C. And once we've got the vector C, then we're going to be able to solve for the X because I know that UX equals C. And that means that I can do another back substitution pretty quickly because U is also triangular. Remember that triangular matrices make back substitution really easy because I can just list off sequentially what the solving for the different components one at a time. So that's really convenient. The big thing is, of course, how the heck do we write a matrix A in this form? Because it seems like it would be a really advantageous thing to do. And it turns out that what you need to do that is nothing more than recognizing the steps that you would need to take to reduce that A down. And we're going to see that it's really not that hard to do. So let's see how. Constructing the L and U matrices come from steps in the Gaussian elimination process. So L can be crafted by considering the elimination steps that come from performing Gaussian elimination on the A. So I want you to consider this really simple 2x2 example, and you'll see like right in front of your face how this goes. So suppose we have this matrix right here. Okay, I'm going to use a row operation of a very particular form, and we're going to see what that does to the matrices. So if I say let row 2 be replaced by row 2 minus a third row 1. Okay, check what that does. 1 minus a third of 3 is 1, so 1 minus 1 is 0. That puts a 0 down here, no problem. Okay, doing the same thing over here, 2 minus a third of 9 would be 2 minus 3, which is negative 1. So that's what I get down here. That should be pretty straightforward to see that is. Okay, I want you to observe a couple things now. This here is upper triangular. And that is a matrix that I'm going to put right here. This is upper triangular. The triangle, that's when you're really angry at a triangle, I guess. Triangular. We're going to call it U. And this here is another matrix. And I want to explain what it is. You notice that we have this diagonal of 1s that appear here. This and this. That's always going to be there for the matrices that we construct. This 1/3 comes from this 1/3 right there. So I'm going to put this, like a little, let's see, a box around this 1/3. And I'm going to draw it down here and put a little box around this 1/3 right there. Okay. It's important, okay, that we have the right row operation to make this happen. So it has to be row 2 minus a number row 1 to put a 0 in this spot. And then we're going to take that number, that 1/3, and we're going to put it in the same spot that we used to eliminate that 0. So the first matrix is a lower triangular matrix L that includes a diagonal of 1 entries as well as the 1/3 we used in the reduction step. So this here is the lower triangular matrix, and we're going to call it L. Okay, and we're going to actually perform the step. It says, then behold, if I multiply these matrices back together, you need to remember how matrix multiplication works, but I need to take this row times this column to start, and that's going to be 1 times 3 plus 0 times 0, that's 3. I get 1, now this one times that one, it's going to be 1 times 9 plus 0 times negative 1, so I get the 9 right there. If I do 1/3, 1, 3, and 0, that's going to give me 1/3 times 3 is 1, and plus 1 times 0. And then finally 1/3 times 9 minus 1 is 3 minus 1 is 2. And all of the calculations that I kind of just spouted off there in the last 15 seconds or so are really familiar because they emulate what we just did with the row operation. In fact, it's undoing it in some sort of sense. This here is how it works. You're always going to get back our A by decomposing the matrices in this way where the lower triangular matrix is given by the number that you use to reduce it down. The reduced down matrix is your U. This other matrix that we craft is your L. And by some matrix properties, you get back our original matrix when you multiply those together. And it's pretty cool. And it actually extends to higher dimensional matrices as well. We're going to see that in an example. So this is going to be a little bit of It's a little bit hand wavy, but a lot of the reasoning behind this comes down to some pretty straightforward matrix properties. There are a few that talk about, when you have particular entries in certain slots and zeros everywhere else in a diagonal, you can take for granted certain aspects about products of matrices and so on. Your textbook goes into a little more detail about this, but it's mostly review stuff from last year. If you're interested in going back and looking at those derivations or justifications, you're more than welcome to do so. Okay, but you can take for granted that with that particular row operation, it has to be the right kind, where you take the current row and you subtract the pivot, which is a little bit backwards from how I usually do it, but that's okay. The number that goes right here, the k, is the number that goes into the corresponding location to give us that L matrix. So yeah, in the end, once you've got that broken down, then we can use it to solve a system in a sort of different way. And it's pretty interesting. And it turns out that it produces a savings of work, especially for large matrices. Okay, so let's do another example here. This is our system from before, from the last lecture. And so what we're going to do this time is take the same system. We're going to find an LU factorization for the linear system that we get, and we're going to use it to solve the system of equations in that sort of like two-step substitution approach, so you can see how it works. We know what the solution should be because we solved it last time. So we'll know what to aim for. So this system is represented by, I'll write it out one more time, and I'll show you the difference in this approach. So 1, -1, -2, 3, 1, 1, 1, -4, and 1, augmented with -7, 14, -25. Okay, so what we did with Gaussian elimination was take this augmented matrix and perform row operations on all the different entries and the right-hand side in order to get to a row echelon form that we could work with to do some substitutions and find the answer. No problem, we know about this. Okay, so rather than that, we're going to do something different. So rather than perform the usual row operations, we will instead seek an LU decomposition for the matrix, and it's not going to be the whole thing. It's only going to be the left-hand side. That's square matrix. That's where there's going to be savings, especially for very large matrices, because we're never going to have to deal with row reduction of those guys. Okay, it's going to be the matrix A equals the left-hand side. So 1, -1, -2, 3, 1, 1, 1, -4, and 1. Okay, because then what we're going to have here is, right, where we had AX equals B right here. Instead, if I factorize this one, I'm going to get LUX equals B. And this vector we can find if UX equals some other vector, which we call C or something. We can solve for, we can solve for the C by using LC equals B. And then once we have that, we can solve for the X by using UX equals C. And in that two-step process, get to the variables that solve the system. So that's how it's going to work. And let me put that in a little bit of a cloud, so you can remember that. And let's go to the next page and actually do this. So again, the L, what the L is going to be determined by the row operations of a particular form that we would need to do to reduce A down to a row echelon sort of form. So let's find our U. Let's find both, really. So row reducing A. We get the following. Okay, so let's see here. What we have to do is use that particular form. So I'm going to keep the top row. That's going to be our pivot for the start. And I'm going to keep a careful record of the row operations that I'm using here. So let's see. The first one that I need to do is, and thinking of the form that I said from before, it needs to be the current row and then subtracting a number times the pivot. So it has to be, in particular, row 2, if I have the 3 here, and I need to subtract 3 times the pivot row. So row 2 minus 3 row 1. Okay, so that is going to put a 0 right there, which is what we want. And then let's see here. If I take row 2 minus 3 of those, it's 1 minus 3 times negative 1 is 1 plus 3 is 4. So I'm going to put a 4 right here. And let's see. I am going to have row 2 minus 3 of these is 1 minus 3 times negative 2 is going to be plus 7. And there's no right side, right? There's no right side to even worry about here. And that's the beauty. That's the beauty. Okay, let's think about the bottom row. The bottom row is going to be I need to take 1, and I need to subtract 1 times the top row. So it's going to be row 3 minus, and the number, the magic number here is going to be a 1. Row 1. I'm writing that for a reason, but if we do that, I'm just subtracting row 3 minus row 1, and that's going to be a 0 right there. Not too hard here. Minus 3 right here. And 1 minus minus 2 is a plus 3 up there. Okay, so a couple things I want to take note of before I move on. I'm going to put a box around this 3 so we remember that that's going to be in the last matrix. And I'm going to put a box around this 1 to let you know that's going to be in the last matrix. We're going to construct that on this side. We have one more step though, because we still have to eliminate this entry right here. So let's do that. And again, it has to be a pretty careful operation because it needs to be of a particular form. We're not touching the top row. That's good. We're not touching the second row. That's our pivot. And the third row, we're going to take, again, it needs to be the current row. So row 3, and then minus some multiple of this row. So I need to take some multiple of 4. That's going to bring me down to 0 here. And I think that the magic number is going to be, let's see here, row 3, minus 3. I need to subtract negative 3/4 of the second row, I believe. Right? I think that's what it needs to be. So minus 3/4 times row 2. Right? So like to make this work, you have to be careful because you can't go like 3 row 3 minus or a plus row or 4 row 2 or something like that, or whatever it needs, or 4 row 3 4 row 3 plus 3 row 2, something like that. You have to make sure that the coefficients are in the right place. Or if you do that, you have to know kind of what that would correspond to right here. Writing it in this way, make sure that you get this right. So minus 3/4 will be the number here. Of course, we get a 0 here. Just redoing it right, making absolutely sure, you're going to get minus 3, that's row 3, and then plus 3/4 of the 4 up here is going to give you 0. So that's good. This bottom right entry is going to be a little bit awkward, so let's do some math. Row 3 is 3, and if I add 3/4 times 7, what the heck is that? 21 over 4, and 3 is 12 over 4, so I think it's 33 over 4, which agrees with my notes. So I think we get 33 over 4 if we do that very carefully. All right. And I'm going to take that number that we used, that minus 3/4, and I'm going to put a box around that. And I want to kind of point out the different entries that we used, right? So this one right here, this row operation is the row operation that we used to put a 0 right there. This one right here was the row operation that we used to put a 0 right here. And finally, this one in that next step was the one that we used to put a 0 right there. So what I'm going to do is off to the side, construct an L. And the L is taken from those numbers. So L is equal to, and remember how it's constructed, we have a diagonal of 1s, 3-dimensional because we're working with 3s. It's all 0s to the right and above. Okay? And the entries in L that are non-zero, besides the diagonal, are going to be the 3 that goes here, the 1 that goes here, and a negative 3/4 that goes right there. Okay. And this here is the L, and this here is our U. Okay. So now what we have to do is solve the following. We reduced the A, we kind of factored it down into 2 matrices multiplied together. And so we're going to solve LU x equals C. So LU is going to be 1, 0, 0, 3, 1, 0, 1, negative 3/4, and 1. The U we found was right here, 1, negative 1, negative 2, 0, 4, 7, 0, 0, 33/4. Okay, this is going to be multiplied by x1, x2, x3. And the original vector that we had was, negative 7, 14, and 25, if we look back to the last page. Okay, and here are the 2 steps. This here, this product right here, is going to equal some C. What we can do is figure out what C is by using this matrix and this value right there. Because look it, I have 1 times whatever C1 is equals negative 7. And so I know that C1 has to be negative 7. C1 times 1 is negative 7. And I immediately know that C1 is going to be negative 7. I can use that to find C2 using these 2 coefficients. And then we can back substitute and find the last ones. So you see, I can take those values of C and figure out what those are. So from, I'm going to run out of room here, but we'll try to make this work. So we're going to solve. We're going to first solve L times C equals B. And this here is the L, and this here is the B, and this here is the C in the middle. And from row one, we have, if it distracts you to see those matrices, just write C1, C2, C3 there instead, right? Instead of all this, and then you'll be able to see, right? If you write C1, C2, C3, you'll have 1 times C1 equals negative 7. That's what the top row says. Because of the zeros and zeros here. And then you can use the second row and so on. So from row 1, C1 equals negative 7. No problem. Okay, let's do row 2. From row 2, we're going to have 3 times C1 plus 1 times C2 equals 14. So 3C1 plus C2 equals 14. C1 is negative 7, so it looks like we're going to get negative 21. Oh, this is supposed to be negative 25. Sorry. Negative 21 plus C2 equals 14. That's going to give us C2 equals 14 plus 21, which is 35. Okay, and then we can take those and put them into row 3. And row 3 tells us that 1 C1 minus 3/4 C2. So C1 minus 3/4 C2 plus C3 is equal to negative 25. And so if you substitute in what we have here, C1 is negative 7. And then minus 3/4 times our 35 plus C3 equals negative 25. That looks like just 25 again, so just be careful about those negative signs. They're very easy to mess up. If you work this out, let's see, minus 25 I'm taking over a 7, so I'm at minus 18. And then I'm taking 105 over 4. Oh, good God. 105 over 4. And 18 is 72 over 4. If you subtract that, I think we end up with 33 over 4. So that's interesting, right? That sounds familiar. Yeah, my notes say the same thing. So C3 is 33 over 4, if you work that out carefully. So that tells us we've got C1, C2, C3, and now we can use that to determine the last the values of x1, x2, and x3. So with, I wish I wasn't so squeezed in here, but I've never done these notes before, so we can use C1, C2, C3 to solve. We need this quantity right here, which is our u times x to equal c. I now know what c is. I have the u. It's right there. And so you see, I can use these to solve for the x. But I'm going to be really careful because I need to make sure that it's all related. So you see, the row 3 here is going to have a 33 over 4 x3 equals the c. And c is 33 over 4. Look at how nicely that works out. So we're solving ux equals c. And from row 3, we're going to get that 33 over 4 x3 equals, and then c3, not the minus 25. We've dealt with this, right? That's taken care of. Now we're dealing with ux equals c, and we found those c's. It's a two-step substitution. And c3 is 33 over 4. And so that means that x3 is equal to 1. And that makes us feel good because that's what we solved it to be before. Okay, from row 2. From row 2, we needed 4c2 plus 7c3, 4x2 plus 7x3 to be equal to c2, which is 35. So we need that to be true. So 4x2 plus 7x3 equals our c2, which is 35. We found x3 to be 1, and if x3 is 1, then that means we take over a 7 here, and we get 4x2 equals 28, which means that x2 is equal to 7. Just doing a little bit of algebra, and you'll remember that x2 equals 7 was the answer that we got in that last lecture. Okay, finally, from row 1, let's take a look. We have 1, minus 1, and minus 2, so we have x1 minus x2 plus, or no, that's not it. It's minus 2x3. That has to equal our c1 that we found. It's top row. That's minus 7. And we found x2 and x3 now, so we have x1 minus 7 minus 2 times 1 equals negative 7. The minus 7's cancel out. 2 comes over. We get x1 equals 2. And look at that. Those are the answers that we found before. x1 is 2, x2 is 7, x3 is 1. And we say, woohoo, we're done. Okay, you might be asking right now yourself, like, why the heck would we do this? It seems so complicated. What was wrong with just Gaussian elimination? Because, like, this seems like so many extra steps. Okay, and I'll tell you why. Because what we're dealing with right now is a very small matrix. And so we're really seeing and feeling the extra steps of that double substitution. But one of the big things about regular Gaussian elimination is there's great computational expense in doing those row operations and doing the calculations for each of the entries. And by saving that whole row, the whole column, right? The B here is not involved with anything. And it's, as a matter of fact, doing these back substitutions tends to be much more efficient because we can do it sequentially. So what you find is that the number of steps required to come to a solution is actually reduced in order. So You remember that from the last lecture, to use Gaussian elimination, the number of steps increases on the order of n cubed. That means if I were to double the size of a matrix, double the dimensions of a matrix from like 2 by 2 to 4 by 4, I'm generally increasing the number of steps I would require to evaluate to find a solution by a factor of 8. Okay? If I were to triple the size of a matrix, I would be increasing the number of steps by a factor of 27. And that gets really big really quickly because of all the different operations that are involved. By using this method, you actually take that n cubed and you reduce it to n squared. You might not notice, right? The number of steps, especially for a small matrix, might be the same or even more. But the fact is that as that matrix scales up, as we deal with bigger and bigger problems, it becomes relatively less work to find the solution as compared to regular Gaussian elimination, which then gives you some computational payoffs, right? So there is some major improvement, especially for large matrices. And I just like you to know how this works. So this is something a little bit different here, and it's some of these matrix methods are really cool, and just wanted to scratch the surface with this. Okay, so as I said, we are just scratching the surface. Hopefully this makes sense. Really, we're just solving or breaking things down into two matrices, breaking a matrix down into two triangular matrices, and then doing two back substitutions instead of one. One to find this C vector, and then one to find the final X. But there's so much more. We're not going to get around to some of these, but it's okay because we're running this final project idea this year, and a lot of you are having a really good time of it. I've spoken to some groups that are excited about their projects and others who have come to some really neat ideas. And some of those ideas are actually matrix methods that some of you have seen. I want to list some of the possible improvements and other extensions and so on that we won't discuss this year, but that aren't too hard to extend a little bit further to see. If you are interested in learning more, your textbook goes into more detail, and any of these are pretty easy to research online if you're interested. Okay, so this decomposition, this LU factorization or decomposition, there are further improvements. Basically, this method right here works on some but not all matrices, and you can expand the amount that you consider by introducing what's called partial pivoting and the act of swapping rows. In doing that, you can, they tend to call it something different as PA equals LU factorization, which involves a couple of extra considerations and steps along the way just to make the scheme a bit more flexible. Another act entirely, another method, another approach that's completely different, but is something that's sort of familiar and really darn cool, is that there are iterative methods. A couple of examples of these are Gauss-Seidel and the Jacobi method, and these provide sequences of estimates of solutions to a system that converge to a solution. So imagine that, I want you to think back to when we were talking about fixed point theory from early in the semester. Iterating a function again and again and again and again can make a sequence of estimates that converge towards a fixed point. The same thing can actually happen with systems of equations, where you get a sequence of estimates, but you get a vector of estimates. And the more you iterate a particular operator, you get closer and closer and closer to the true vector. So it's really just the same thing as fixed point theory, but in sort of an analogous matrix approach. And that's really, really interesting. So it's very similar to what we talked about with fixed point iteration before, except with vectors. And finally, there are methods similar to Newton's method, and one of the famous ones is called Broyden's method. So many people's names to remember and so on, that are usable to approximate the solutions to a nonlinear system of equations. There are lots of systems of equations out there that can't be represented as a linear system. If you can't represent a system as a linear equation, that means you can't write it in terms of matrices, or you can't easily do so in the traditional way that we do. But if that's so, you have to consider some other approach. And so this gives us sort of a way that mimics Newton's method, except for systems of equations with maybe more complicated functions involved. And again, I talked to a few groups that have worked on all of these topics as part of their projects, and I hope that you're learning lots. But I just wanted to give you a little bit of a broad overview of some of those things that we could have gotten to if we had a little bit more time, but I think we did pretty well this year. Yeah, so let's wrap this up. First of all, I want to thank all of you for your patience through another tough year. I hope that despite the change of pace, and like this was an unusual offering, I hope that you felt like you were able to learn something. I've talked to a lot of people who are basically afraid of coding to start with, who have come around and feel like they've improved a lot. If that's true, that means a ton to me, and I'm really proud of you for sticking that out. I also want to just thank you for your patience and your willingness to communicate with me and use the resources available to you. The comments on YouTube, the comments through email, the questions that I get, and the great times we have in lab together have been really, really awesome. So I just want to say thank you very much. And I want to wish you all very well on your exams in this course and in all of your courses. And yeah, take care of yourselves and take care of each other. And I hope to see you on campus sometime sooner than later. All right. Goodbye, everybody.